You can discover more about a person in an hour of play than a year of conversation. I was lucky enough to spend time with Joe Armstrong on the piano, playing with ideas both musical and programmatic. There was one time that we were sitting there and we were talking about the naming of motifs, the naming of bars. Can we hash them and can we get their names? And during that session, he told me one of his favorite quotes by T.S. Eliot. And so I decided to calligraph it and bring it to him the next year. Joe was the music while the music lasted. If anyone tried to converse with him, he would play over them, usually, and steal the stage. If you know Joe, that's how it went. And one of the ideas that we're going to play with today is conference-driven development, something he was trying to do the whole time I met him. He was convinced that's the way conference talk should go. They shouldn't be me lecturing you. They should be me giving us problems that we can solve as a group. And so that is what we're going to do today. I hope that I give you more problems than I do solutions, even though I'm going to give you a couple graphixes, so to speak, fixes of our Erlang digraph ecosystem. So yeah, please email me at 2020@scriptculture.com with comments. I encourage you to talk with each other after the conference, for tomorrow and throughout the rest of the conference. And please get back to me, and I will send everything from this conference to you, or from this presentation to you at the same time, and keep you up to date as things go on, because I can get your email from a mailing list. So let me summarize where we are, or where we were, and what I went over, and where we're going to continue to go. My first talk was wxErlang and faithful representation, or representational faithfulness, which was when we went over the accounting conceptual framework, and we looked at how Erlang and the accounting tenets are in line. In fact, Erlang is a fantastic language for accounting. All accountants, I encourage you to use Erlang, and all Erlangers, go check out accounting. You already do it. Then we went over we went over the wx style text control in composing in style. And the focus was on continuous versus discrete. That is, when you compose, it's a continuous activity. It's not discrete clusters. Even if you have a bunch of discrete clusters, you have to recompose them in another continuous activity. That is the nature of it. And for the next talk, or should I say two talks, because that's it's broken into, we're going to be going over group theory and graphs. The second talk I'm going to be giving sometime hopefully later this year is the alchemists of their Erlangen program. It's a mathematical paper. The mathematician Klein talked about group theory, brought together a lot of basically the beginnings of algebraic geometry. And hopefully at the end of this talk, I'll be getting into metric spaces and topology, and how and the Astar algorithm, we need that for. We need metric spaces, and the distance function is what's very important there. But today, it is your Erlang graph fix. So let's go over a quick roadmap of today. Again, what is a graphics? It's a problem I'm going to be giving you, and talk about it, think about it amongst each other. And for all the YouTubers out there, the talk is broken into pretty much 5 minutes for the beginners, 5 minutes intermediate discussion, philosophy, and then 5 minutes we'll be wrapping up with a really big graphics alongside the Astar algorithm. So what is a digraph to an Erlanger? It's first on the bottom here, it's a tuple of 5 elements. The first element is the atom digraph, and then we have 3 ETS tables. And that last one that says true is the cyclicality of the digraph. Loops, if you've ever tried to parse a loop, computers don't like loops. So that tells us if the digraph is cyclical or not. In addition, this format of a digraph is called the collection of adjacent lists. There's actually another format for you can make digraphs in, which is the adjacency matrix, where you have it looks much more like this, where you have the vertices on top and bottom, and then you have the connections either on or off as the given places in that adjacency matrix. That's what a digraph, which hopefully we want to incorporate. That's another problem. We can't actually do adjacency matrices with in that object of a digraph. So what is a digraph to a layman? It's basically anything you can capture with a bunch of lines and a bunch of dots. Essentially information asymmetry and just information entropy in itself. The whole domain of graph theory is very complex, so much that some of the luminaries in the field don't even have an agreement upon what a graph is. There's disagreements. Not surprising. There's to the fact that there's a conflicting school of thought. We actually have a major faux pas in our digraph library. According to the Jensen and Guten, we have when you have a digraph, you don't call it an edge. You call it an arc. It's only when you have a unidirectional or undirected digraph or a mixed graph where you have both unidirectional and just directional arrow edges or arcs that you can actually call it an edge. So our first graphics here is that we've named it wrong if we're actually meaning digraphs when we say digraph library. So think about that again and talk amongst yourselves whether we should be changing this or not. If we want to actually connect to the larger discipline of graph theory, we're going to really get into because it's a huge field. We might want to get the basics correct. And another thing Joe taught me was, and I think this is just general knowledge in computer science, is that the two toughest problems in computer science are what to name things and what to cache. So, we just got caught in a very difficult problem here. And speaking of naming things wrong, so here's our digraph library. I edited the whole thing. Again, email me and I'll just give you an edited digraph library so you can read through it if you're a beginner. This is a great way to learn. If you're advanced, you don't know it. I have all the documentation right next to the functions. This is how I like my functions. And there you can see the 3 ETS tables being built. But we do have an issue. The library, the digraph library, is wrapped and looks like 3 ETS tables. That is, even the add vertex function, which calls do add vertex, and down here you can see it just basically wraps the ETS insert function, essentially is used to both add a vertex and update a vertex, which is extremely confusing for a beginner trying to use the library. I think we should address this and actually not have the API look like a bunch of ETS tables, but also have it be built so that we actually have a given API for a graph that, hence get a set function, a new perhaps, that makes a new vertice. We'll get into that in a little bit. And so you can see I edited all these libraries. Again, email me if you want them. I also edited the ETS library as well. Very nicely, so that if you don't know ETS tables, give me a shout too. And I think it's a good way to learn how ETS tables work, much better than trying to pick through it or read the documentation. I'm into the agile, everything in the source philosophy. As we said, it looks like we're going to wrap the digraph library here because we want to go change some names of the functions. What else can we do if we're going to wrap the digraph library? And again, I encourage you all to actually read this, and I challenge you to wrap your own. You're going to learn how the digraph library works very quickly if you just go and you rewrite it once yourself. It takes no more than a couple hours to really read through it, especially with the edited. You'll learn it quick, and you'll find at the end of that, you're going to want to actually make your own digraph data type. And that leads us to another graphics that we're going to want to try to implement, which is that we have a structure to digraphs, this guy with the 3 references. We want to actually, I think Howard Moskowitz said there's no perfect Pepsi, only perfect Pepsis. I don't think the Pepsi people are here. But the fact of the matter is that there's no perfect digraph format. The right digraph format is the one that you want to use, the one that I want to use, the one that we all want to use and make for ourselves, not one that we actually have to conform to an object. That's very non-Erlang way of actually approaching the issue. So yeah, go wrap the library. When we also wrap that library, we can also fix another huge problem that happens to beginners, which is that when you spawn a new digraph library and you try to add a new vertice or something and you actually mess up, of course you crash your shell. And because you crash your shell, you also kill all the ETS tables. So everything you were built and trying to learn basically is destroyed. So we can go and take at the very top of the digraph library and just implement a catch function so that instead of actually crashing the shell when you're using it, you can go and you can catch that exit message instead of having it crash your shell. And so you can actually update and utilize and learn how the digraph library works without it destroying all your data right off the bat. That's a huge help to learning it. We'll get into this digraph geometry, this DGO thing in a sec. So yeah, before we move on, I just want to jump quickly into the other digraph tools that are out there. Just so and I won't go into them too much as the most popular one is the digraph visual description language that jumps into GraphViz. There's a library Erlang GraphViz converter out there that if you have a digraph, it's a pretty simple language. It's pretty much an arrow between two vertices, and you don't even need to define your vertices. It just basically sources all the vertices and assumes that those vertices are the vertices, and we'll build a graph out of that. In addition, there's a couple other tools down here you can check out. GraphErl. In particular, Rec was a library that was proposed a couple years ago by Richard Kalos, and what he made, it was a great wrapper of dependency graphs, but he made you make a module for a given vertex, and so the question is, does a given vertex need a can we get rid of that module, that dependent module that you need to actually define a vertex? The question is, what is a vertex? Now okay, so and this is a question that plagued me for months. As soon as I put my talk in in October when I gave my talk, and I was just thinking, what is a vertex? And I ask you that question right now. Can you all think of what a vertex is? Can you answer that question? People on YouTube, pause the video before you continue. Try to answer that question. I'll give you all a moment to really answer it, or just come up with some sort of semblance. Now, does that definition you have in your head, is that stuck in one dimension? What happens? Can you add dimensions to that? What happens if two people need to agree on the vertex that you just thought up, whatever that data type is? These are questions that I was thinking about as I made this. My first thing that I thought we needed was a float tag, where it was just some addition of floats per dimension, and we would tag it to the data. And then, of course, I was like, well, no, it just needs to be a reference because I defined it, and I could define those other parameters elsewhere. But then I realized I was tagging the data, and that's not what we wanted to do. That's not what we want to do. Right now, you have no choice because a vertex is just a label. A vertex is a label or I think I can find it quick. It's the vertex name for the ETS table and then a label. And for a graph, it is for an edge, it is the ETS table data type. The ETS table uses the first vertex, which is the emanating vertex, and the second vertex, which is the incident vertex, and then the label. So pretty much it's just that little structure. Anyway, I had a quote here by Joe for the banana quote. Anyway, so that basically it's not you don't want to bring the jungle around with you is what the quote said. It was, you want to go and, you don't want to bring the jungle with you. You don't even want to make object-oriented programming is making the jungle and then bringing the jungle with you if you just wanted a banana. In this case, we just wanted a banana, which was the idea of a data type. So that's all we want is just a data type. We don't actually have to tag the thing or depend on an ETS library, ETS table to actually have our data type and move it around. So it's just a data type through time is what I came up with at that point. And how many of you, and props to you actually, if you thought that when I said what's a vertex and you guys thought it was a little data type through time. Took me a while to get to that point. And I encourage you to think about Peter Van Roy, his talk back in Stockholm, where he said that Erlang could be the best language, but we need to deal with the time problem. I believe that us fixing our digraph library and us fixing this time problem that he's talking about, it's almost one and the same. At least it's one of the major first steps is us just to define something moving through time or a data type moving through time. And but even at that point, the data type through time, because once we establish it as time, it gets side effects. And if it gets side effects, maybe the right data type is just a CRDT. And after all this, I realized that it doesn't matter what the data type is. The fact is that a vertex is just a point of interest. It's something I can hold up and something that you look at and you realize that's something that you want to pay attention to. And then you can start adding data to it. So can we make Erlang have that feature so that we can utilize it? And I mean that feature because I'm talking about dyadic thinking, that the ability, as we go into smart tools, we're going to need this ability to say, hey, that chair, hey, that slide, that picture, that F, that G on the those are all of a sudden they become vertices. The other option is just we start to try to cache everything, and so there is this intimate link between what is time, what do we focus on, and actually how do we go and describe it to the computer so that it can display, it can actually analyze it. And so I started going in this direction because this definitely starts to look like a wrapper library that's wrapped around, a wrapper digraph library that, it brings us back to that geometry, that dgeo function right here. Because if we add that after the catch and we put that in front of every function down here, then, and we put that, oh yeah, it's not anywhere because it's a macro. But if we put that macro in front of all the major functions, here I think they're right here, the DG, what we can do is we can actually analyze the type of a pattern of the digraph we're looking at. And then all we need to do is actually have a unique type of pattern, and we can actually really abstract all these digraph library types. And this, in my mind, is in the direction of a true graphics, where we can actually abstract that pattern from digraphs. And I also found, when I was getting into this, there's this OCaml library that they made a while ago, and they did just that. They abstracted, here's the paper, Designing a Generic Graph Library using functors, which, by the way, for all the beginners out there, functor is just something that can be mapped over. It's a map function. I'll just make that easy for you. And so this is what their structure is. Where first they ask whether the graph is persistent or imperative. Basically, is it a CRDT or not? Is kind of in our speak. Does it actually have time? Can it be a CRDT? And then they start breaking it apart based on labels. And we have a one-up on OCaml here. We have concurrency, and they don't. We can actually abstract a lot of the patterns that they came up with 19 different patterns for graphs. We can abstract a lot of this out, and I believe we can abstract all of it out into just one digraph library that can analyze patterns and find out how. And in this way, we only need to write in our libraries simple functions like get vertex, add vertex. I mean, all the basics here is all we're going to have to write for our digraph library, and then hopefully after that we can actually abstract these large, like components, strong components, these more complex functions, and just reutilize them. And so that we don't need to rewrite that portion of it. There's actually a very few amount of functions we need to actually write that encapsulates interaction and the API with that graph library. And so Erlangers in the audience, I encourage you to go read How to Bind to Elixir because they have a fantastic matrix library called Matrix. And if you haven't done yet, Joe has a great blog post. The last blog post he posted, it tells you how to do that. And for the Elixirists in the audience, I challenge you to go and wrap this digraph library. It will teach you Erlang. We need to start bringing the two communities together. And this is a great example of, we didn't have a good matrix library in Erlang, and all of a sudden I bound to Elixir and I had a fantastic matrix library and I could utilize it. And vice versa, this is a way where Elixirists can actually come and give their data types to Erlang and have it available to all, Erlang and Elixir alike. So I challenge you to do that, and that's a problem we have. And this leads us into a whole bunch of future problems we can get into, like what is an edge, not as just what is a vertex. I can tell you that what an edge-centric graph is used for is parallel processing. And so you can just imagine what we can utilize it for with concurrency, having an edge-centric graph. So let's jump into the A-star, and we'll close really briefly, and we'll close up. Yeah. 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 So the A-star algorithm is a. Yeah. Okay. Yeah. The A-star algorithm is a search algorithm. There's breadth first and depth first. Go look on basic YouTube videos for those. But the A-star is essentially there's 7 major functions here. It's basically a vertex grabber, an edge grabber, a goal function, sum, combination, and then a main one that just takes those functions and pulls them together. And so it's a lot like a QLC data type. It's just a bunch of anonymous functions. But the neat thing that I really wanted to bring up here is that if we go and we wrap the digraph library in the way I said, we can basically just have it automatically grab the get function from the vertice. We can have it grab the get function from the edge, so we don't need to write those. We actually, because if we can define a graph, because what I was getting at with the diketic bit was that it's me, or it's you and a piece of data. The graph and the topology ends up being you, and and your piece of data ends up being the thing you're pointing at. So that essentially the contract between the two ends up being a topology, which you can measure with a distance function. And with that distance function, we can also get away with the goal function in the A-star algorithm. And I believe that this is going to be the story for a lot of graph theory with Erlang, is that we can basically abstract almost all or a lot of the patterns more than any other language away with this method. And this A-star algorithm shows you that can be done. So in conclusion here, just remember Erlang and Elixir is something that you carry with you. It's not something you do. It's something you bring with you. And your vertices in that matter are something that you bring with you, and your perceptions through time are something you bring with you. Joe is obsessed with making sure that we hold on to our history. And so I wish you all to be, and I encourage you to be the music and make it last.
It's on. We still have time if no one is needing to rush out for Q&A. Just had to keep things on schedule.
Yeah.
If anyone has any questions, we probably don't need to use the mic. It's probably a small enough room. Any questions, anyone? I'm sure there's quite a few. Graphs are pretty fun. Okay.
Yeah, we don't need any. I mean, well, yeah, that's exactly the point, is that you should be able to make a digraph of however you want and use one interface so it's ubiquitous. Yeah, I was going to say, if you look at Hype, I cut this out. Hype actually has a digraph in it. It spit up our compiler, if you don't know what Hype is. And they use it's right here. They use just basic sets, right? And Wings as well has a completely different, Wings vertice. They have a completely different, sorry guys. a completely different function. Oh yeah, it's right here, sorry. Oh, it's the 3D library. Yeah, they have a completely different take on how you should look at a vertex. But shouldn't we be able to bind to one of their vertexes just in terms of get and set, just so we can see how the inner workings work? It's very possible. And I'm going to be working on it. So if anybody wants to continue to work on it, just give me an email at 2020@scriptculture.com, and I'll send you the current state of things, and I will keep you up to date with where this project is. Yeah. Oh no, this is Don Gunmundsson's from Sweden. He wrote the wxErlang library alongside us. Oh yeah, that's mine. Yeah, I think I'm sure. I mean, a completely different subject, but I really believe that that Erlang code can be beautiful if we format it correctly, and it's readable and it's quick. Oh, I mean, well, you can see all the functions very nicely top down. The commas over on the left-hand side give you, the main concept is to lead the eye like a good piece of artwork. Care about your audience reading your libraries to make sure that you show them where to look. Erlang has a lot of symmetry when you get into it, where you're just changing one or two things in a function, or maybe you're adding an extra argument, and you want to exemplify that when you're writing your functions so that the reader can just quickly see what's going on versus having everything kind of, we can go to the ets table or a better, yeah, it flops either way, in all honesty. Sometimes it's nice all the way out to the right so you don't even have to deal with it. Usually I like it before what's going on. So for instance, in a guard, you can say and or if it's a semicolon. So you can just tell the person really quickly, and you can see the logic on the left-hand side. It reads a lot quicker. Well, that's a good thing in art. You should be using the white space to let the users or let the individual's eye actually trail around the piece of artwork. Yeah, Joe talked to me about that too, where it's possible to make Erlang code beautiful in that way, and really, I think we can engage the greater community. Erlang is such a small, condensed language that I strongly believe when it comes, when we're wearing our local area network and everyone has a distributed set of smart tools, Erlang and Elixir are going to be the ones that are the most practical to be using on a day-to-day basis. It's the smallest language. It's easiest for everyone to learn. Yeah. Thank you.